All right. So on Monday, so a couple days ago, we started just by talking about z-score and the bell curve. Okay. Um, and so that's the an introduction into the standard normal distribution. And we talked a little bit about z-scores, but we didn't talk a whole lot about what they mean, right? They have something to do with standard deviations and averages and means, um, and that's all well and fine. But really, the goal of the standard normal is that we're able to come up with a probability for something, right? So, um, I don't know, let's say that the chances that your flight get delayed are um, distributed normally, and so they fit on a normal distribution on a bell curve, and that's why that is, or why that works is not necessarily the big idea right now, but it would be nice to know, okay, well, oh, my flight has a 10% chance of being delayed, right, or something like that. Now, maybe flights wasn't the best idea because uh, generally when things are running well, the flights being delayed or not normally distributed. Not 50% of flights are being delayed, but um, maybe you think about test scores when they're distributed about a mean, or maybe we could look at how long flights are delayed, right? Maybe even if it's 5 minutes, maybe that counts. And what are the chances that your flight's delayed more than 10 minutes or more than an hour or something like that, where we can look at this table and start to get probabilities and percentages. And it turns out that a lot of times when you have a high population, um, or you have a lot of data, so a high population just meaning that we took data from a lot of people, a lot of the times it'll start to look like a normal distribution as we get more and more data, and it'll start to fit that way. And that's not always the case, but it happens frequently enough that one of the most beneficial things that you can know from statistics, whether you um, study statistics or not, is to have a general idea of what a normal distribution is and what a bell curve is and how that kind of relates to probability, right? So today I want us to take a step in that direction and kind of link normal distributions, z-scores, bell curves, and probability. Okay, and so a normal distribution we use and we represent using the bell curve. So this should be a review from the other day. But if I have a bell curve, right, you'll recall that the middle of the bell curve, directly in the middle, is mu, which is also the mean, which is also the average, depending on which terminology you prefer, right? We also have what we call the standard deviation, which measures variance, which we called sigma. That's the standard deviation. Now, when we look at the bell curve of a normal distribution, we want to look at the amount of standard deviations we are away from the mean, right? So, for example, if the mean is 0, right? So mu is 0, standard deviation is 1. If I'm one standard deviation away from 0, then I'm at 1, right? If I'm 2 standard deviations away, then that's 2. If I'm 3 standard deviations away, then that's 3, right? And alternatively, we could go in the other direction. I'm a standard deviation to the left, 2 standard deviations to the left, or 3, right? Now, we can determine probability by looking at the area under the curve, okay? And generally, if you have a function value, or not a function value, if you have a function, then if you continue on into calculus, you'll see that finding the area under the curve is maybe not overly difficult, but it is a tool that we're still a few years away from having. And so what we have is this tool called a standard normal table, and we will learn how to use that to find area under a curve. Okay, so just starting out with a common sense check, right? If I'm looking at a standard normal distribution here, then I can expect that 50% of the data is going to be above the mean and 50% is going to be below. So representing that visually, that means that 50% of the data is here below the mean, right? And the other 50% is above the mean, which doesn't tell us a whole lot, right? If you tell someone, oh, you have a 50% chance of being, you know, you have a 50% chance of passing, or you have a 50% chance of not passing. That doesn't tell you anything, right? That's just a yes or no. That's a binary question. 50-50 is maybe one of my least favorite terms because it says almost nothing, right? You say you have a 50-50 chance, well, it's either going to happen or it's not going to happen. There's no skew in terms of this option is more likely, and so that doesn't tell us a whole lot, right? If the scores are normally distributed and the mean is a 68, then you have a 50% chance of getting above and a 50% chance of getting below. Okay, great. That's told me nothing, right? What we really want to do is look at ranges, right? What are the chances? Okay, well, if the average is a 68, then what are the chances that I get below a 60, right? What are the chances that I fail the test? Or on the other side, what are the chances that I get an 80? What are the chances I get a B? What are the chances I get an A? Something like that, where the probabilities are not necessarily 50-50, right? And so to do that, it's important that we do look at our standard deviations here, okay? So looking at a bell curve, draw a little bit bigger, maybe not the best in the world, but oops, that's not what I wanted. So once again, mu, one standard deviation away, two standard deviations, three standard deviations. Okay, so we really look at those three standard deviations in either direction because that's where the majority of the data is going to fall. And so if we have a true standard normal distribution, if you're told that something is normally distributed, then it actually turns out that, make sure I get this colored in right, let's do yellow. That means that 68% of the data falls within one standard deviation. Okay, so 68% of the data, and that's a really bad 68, and I apologize for that. But 68% of the data falls in between the first two standard deviations. So essentially what that means is if our average test score was 68% out of 100, actually we'll change that just so this isn't more confusing than it needs to be. Let's say that the average score was a 72, how about 75? Nice solid C. And the standard deviation is 3 points. Then 60% of the data, 68% of the data is between one standard deviation lower, which would be 72, right? 72. And 78. So there's a 68% chance that you got somewhere between a 72 and a 78 on the quiz, the test, whatever you want to call it, right? The next two, so now we looked at one standard deviation. Now if we look at two standard deviations, okay, so within two standard deviations, in this case, 95% of the data falls within two standard deviations, right? So now you have a 95% chance that your test score was between a 69 and an 81, right? So assuming that our test was normally distributed, you have a 95% chance of getting between a 69 and an 81. That's pretty good, right? The 95% of my students are passing, and not only passing, but passing with, most likely a C here, which is, pretty good. Not too mad about that. Okay, which is great. That's a high test average. That's a small standard deviation. If we increase the standard deviation, then you would see a wider range, right? But as it turns out, the average was 75, and a lot of people were close to that, so the standard deviation was relatively small. Okay. The third one we'll look at is our third standard deviation out. So all of this in here. That is a 99.7% chance. So you have a 99.7% chance that your score is between a 66 and an 84, right? Now, I didn't just come up with these numbers, okay? These are the true area under the curve values. If you have a standard normal and you are within one standard deviation, there's a 68% chance that you're within one standard deviation. If you're within two, then there's a 95% chance. And if you're within three, there's a 99.7% chance. That's not just for this specific example. That's not just for, when we assume a mean is 0 and that a standard deviation is 1. This works for any set of data that is normally distributed. Okay. Now this is all well and good, except for now it's a little bit strange. What if I'm not exactly one standard deviation? What if I'm right here? Slightly more or less than one standard deviation, but I'm still higher than the mean. And I want to say, what are the chances that I get above, or what are the probabilities that I get a 60, what would that be, or a 76 or above, right? And so we want to find this area, and that is where our standard normal table comes in, right? So let's look at how that might work. Okay, so I've got a bell curve here, and we're going to stick with the same example. I have a mean of 75, and so one standard deviation would be 78, 2 would be 81, and 3, 84, and the other direction, 66. Okay, so you say to me, well, Mr. Otterstetter, I need a 76% on this test, so we'll mark that in blue. You need a 76 or above, so we want to find the probability that you got a 76 or above, and so we want to find this blue area. Okay. Now to use a standard normal table, what do I need? Well, I have to have the z-score. Okay, and so you'll recall that the z-score is equal to x minus mu all divided by sigma. So x, and I subtract the mean, and then I divide it by the standard deviation. Well, mu, we already discussed, was 75. Standard deviation is 3. So if your goal is to get a 76, then I'll take 76 minus the mean, which is 75, and divide it by the standard deviation, which which is 1/3, or 0.33. And when we're using standard deviation, we want 2 decimal places, and you'll see why that is in just a moment. Okay, so what this says is that you're 0.33 standard deviations above the mean. Okay, but our goal was to find a probability. So we need to get a standard normal table. So I will link one in your assignment. They're also super easy to pull up. So I will do standard normal table, and we'll just pick that. Okay, and so what it looks like is just a big old sheet of numbers. And what these are, is these are all probabilities. Okay, now recall that our z-score was 0.33, right? So I need to find that z-score on my table. So what you first do is you look for those first two values. So 0.3 in the left column here. So you'll see it starts at negative 3.9 and goes all the way to positive 3.9. We're looking for a positive 0.3. So I find my 0.3 column. And then once I found my 0.3 column, the second digit of the decimal was also a 3. So this here, let's see if I can highlight it, would be 0.33. Okay, and what that gives us is, you can read up here, the table values represent area to the left of the z-score. So remember that number, 0.6293. Okay, so we've got 0.6293. Okay, what that is the area below your z-score. So a standard normal table always gives you the area below your z-score. Right, so that area here. Probability is always out of 1, so the entire area here. If I looked at the area under the entire curve, it's total. The probability of anything happening, there's a 100% chance that something's going to happen. That's a probability of 1, right? So if we want the other area, then the blue area plus the green area should add up to 1. So to get the blue area, which is the area we're looking for, then I would take 1 minus the green area. And so 1 minus 0.6293 is 0, oh, forgot to put that in blue, 0.3707. Great. That's a probability, right? But presumably we prefer it to be in a percent. So to get a percent, we multiply it by 100, and that's the same as 37.07%. So you have a 37% of getting higher than a 76 on the quiz. Now, obviously, that doesn't take into account how much you've studied or how much work you've put in, but generally, if people are just coming in to take this test and we assume that they've all done the same amount of preparation or they've all done no preparation, then everybody has the same amount of chances of doing well as doing poorly. Then in that case, you would have a 37.7% chance. Okay. Now, that was a lot of information. That was, not very easy. This video is probably getting pretty long. I can't see a timer. If you need to, now would be a great time to take a break, step away, maybe decompress. I'm going to do one more example just for practice sake, but I don't want you guys to get stressed out or anything like that. So if you need to, do take a break, step away for a little bit, right? So my next example, we're going to look at what would be interesting. Okay, I found some data here for the birth weights of infants. Okay, and for some reason they're in grams, but that's all right. So, first piece of data is that our mean, the average weight of a newborn baby is 3,270 grams. And the standard deviation, so the variation that we're getting between these children's weights, is 600 grams, right? So I'm going to draw a picture because that helps me, and I think that'll help you too. But if you do not want to, then you technically don't need it to solve the problem. So that's the mean. One standard deviation up would be 3870. 2 would be 4470. And 3 would be 50. Right? And the other way would be 2670. And 1470. Okay, so I've got a nice little bell curve there, and the question is going to ask us, what are the chances that a baby weighs below 4170? So that's 41. Right. So first thing that I would do is I would go to my graph, right? And I would say, well, below 4170, that's about here, right? It's right in between one standard deviation and two standard deviations, okay? And then what is it asking? Well, it's asking what's the probability that a child weighs below 4170, so it wants this area, okay? So once we find our value in the table, because it always gives us the value or the probability below some z-score, then we won't have to do any extra calculations after that, right? So the only calculation we need to do is finding the z-score. So z-score is x minus mu divided by sigma. So x is the weights that we're looking at, which is 4170. The average weight of a newborn is 3270. And the standard deviation is 600. So that's 300, not 300, sorry, 900, 600, which is 1.50. Do include the 0, because remember, z-scores, we're going to want to have two values, or two decimals, two values after the decimal. Yeah, okay. Let's go to our standard normal table, okay? So standard normal table, we're looking for 1.5. So I'll go to 1.5, oopsies, 1.5, and it's 1.50, so we're going to be in this first column here, and 0.93319. Okay, so that red area, 0.93319. Okay, recall that the entire bell curve is 1, and which also means that this green area plus the red area would give us 1, but we're not looking for the green area, we're looking for the red area. So the red area is 0.93319. That's a probability, or we could write it as a percentage where we multiply by 100, which also just means you move the decimal to the right 2 points, which is 93.32%. So the chance that a baby weighs less than 4170 grams is 93.32%, right? So this has probably been a long video. I'm going to find out when I stop it here in just a minute. So I'm probably only going to give you 1 or 2 problems to do today, and then I'll have more practice on Friday. So do make sure that you understand what's going on here. Maybe have some notes written down for later on. But hopefully this made sense, and if it did not, feel free to reach out to me, or there is so many videos on standard normals on the web that you may be able to find one that makes more sense than what I've said. So let me know if you need any help, and hope you guys are all having a great Wednesday.